Project Planning and Control, PPNC. Planning and Baseline Architecture. Course 2, Module 1, Part 1. Module 1 is the core, everything from Phase A concept development through the Phase BC gate, covering every PPNC planning product required to begin implementation. The key phrase here is executable plan, not a wishful plan, not an optimistic plan, but one you can actually defend at PDR and that will survive the scrutiny of the Standing Review Board. By the end of this module, you should be able to look at any program's planning artifacts and determine whether they're integrated, complete, and realistic, or whether they're setting the project up for early overruns. Planning is the only phase where you can still prevent problems cheaply. Once you're in Phase C, every gap becomes a cost and schedule event. From contract award to an executable baseline. This module focuses on the planning foundation of a government program, covering the process from early concept development through key program approval milestones. Participants will learn the importance of effective planning and the 9-step planning process, along with how to develop a work breakdown structure, estimate costs, and build an executable schedule baseline. The module also introduces earned value management, integrated baseline reviews, risk management, joint confidence level analysis, and contract management practices that help ensure successful program execution. By the end of this module, participants will be able to evaluate whether a program's planning products are complete, integrated, and ready for execution. The course covers key planning components, including work breakdown structures and the 100% rule, cost estimating and basis of estimates, schedule baseline development, and earned value management planning. It also explores integrated baseline reviews, risk management, joint confidence level assessments, and contract management practices that support effective program planning and control. 3 foundational governance principles frame how all government programs move through their life cycle. This is not bureaucracy for its own sake. It is the decision architecture that protects the agency's commitment to Congress. Designated decision authority is the key phrase. Every gate has a specific person accountable for saying yes. As a PPNC professional, your products are what that person evaluates before making that call. Governance provides the checks and balances, independent review, and dissenting opinions exist precisely because programs consistently underestimate technical risk and overestimate workforce efficiency. Programs that treat governance as administrative overhead rather than a decision quality mechanism tend to make the same kinds of errors, as demonstrated in the plan versus actual reality chart. Optimism is embedded from start. Before going into lifecycle phase detail, I want to orient you to where we're headed. PPNC sits at the intersection of planning and control, and everything in this course maps to one of those 2 central functions. The diagram here shows both phases in the context of the full project lifecycle. My 40 years at JPL and Skunkworks taught me one consistent truth. The programs that struggled in control almost always had a planning problem they didn't know about until it was too late. Planning produces the baseline. Control measures performance against it. You cannot do the second well without having done the first rigorously, and that sequencing is exactly how this course is structured. When you finish this course, you'll be able to walk into any program in either phase and know exactly what PPNC should have produced, what it should be doing, and what's missing. The full NASA life cycle from pre-phase A through phase F is depicted here. This is the operating framework that governs when PPNC products are acquired and when they're evaluated. Phases A and B are where you build the plan, and phases C and D are where you execute and control against it. The transition between them, KDPC/PDR, is the single most consequential gate. Every discipline in this course, WBS, estimates, schedule, EVM, risk, IBR, maps to a specific phase requirement. Know where you are in this life cycle, and you'll know exactly what PPNC needs to produce. The life cycle is not linear in practice. Planning is iterative throughout phases A and B. But the gate transitions are real commitments, and once you cross PDR, the rules of the game change completely. This simplified lifecycle chart maps major reviews to phases, from mission concept review through decommissioning, so PP&C professionals understand the review rhythm they're supporting. Reviews consume enormous resources, time, travel, preparation, and rework. The point is that improper planning drives rework, and rework at major reviews is one of the most expensive things a project can do. Each review has specific PP&C evidence requirements. Your cost, schedule, and risk products aren't optional inputs. They're the analytical foundation the review board uses to make its decision. Know which review is coming, what PP&C must produce for it, and whether your current products are review ready. If they're not, you'll be the one explaining why the KDP slipped. KDPC/PDR is the gate that converts a planning program into a committed program. It establishes the agency baseline commitment, ABC, the official JCL, and the integrated cost and schedule baseline. There is only one official baseline for a program, and it is the agency baseline commitment. Everything produced before PDR is in service of creating that one document. The JCL must demonstrate at least 70% confidence that the program can meet its cost and schedule commitments. If it doesn't, you do not pass the gate without significant replanning. All subsequent reviews, CDR, SIR, FRR, are measured against the bar set at KDPC. Get the baseline right at PDR, and you give the program a fighting chance. Get it wrong, and you are explaining divergence for years. Phase A is the conceptual phase in which the program defines what it wants to build, what it needs to know technically, and what resources it will require before any major design work begins. The three major activities, concept development, requirements definition, and preliminary planning, are iterative. You do not finish one before starting the next. They inform each other continuously. At the end of Phase A, the project needs to demonstrate a viable concept with a preliminary resource plan. The specific PP&C deliverables are initial cost estimates, preliminary IMS, and a high-level risk register. Phase A is when you have the most latitude to get the framing right. Assumptions embedded in Phase A estimates tend to persist. They become the heritage data that informs everything downstream. Phase A culminates in KDPA, which approves entry into Phase B. The decision is made based on whether the concept is viable, the plan is credible, and the key risks are understood. TRL 3 to 5 range for technology readiness is the Phase A benchmark. You're not expected to have proven hardware, but you do need to demonstrate that the approach is physically feasible. The preliminary IMS and initial LCCE produced in Phase A become the baseline for the JCL work that culminates at the end of Phase B. The quality of these early products determines how credible your JCL will be. Programs that rush through Phase A to get to real design work often produce shaky cost and schedule estimates that never recover. As I stated earlier, the plan drifts, and that drift starts here. These are the specific PP&C deliverables required in Phase A, not generic planning, but the actual cost estimates, schedule structures, and risk assessments that will feed the formal gate products. Cost estimating in Phase A is inherently top-down and parametric. You use analogy and models because you do not have enough design definition for bottom-up. That's not a weakness. It is appropriate for where you are. The cost analysis data requirements, CADRE, package is the documentation trail that will be reviewed by cost credibility reviewers at PDR. Start it early and maintain it throughout both phases. The IMS built in Phase, it doesn't need to be a 1,000-line network. It needs to capture the key milestones, major deliverables, and logic that shows the project team understands how the work will unfold. Risk integration begins in Phase A, and EVM groundwork is laid even though EVM reporting doesn't start until Phase C. This is the investment in infrastructure that makes implementation possible. The point about EVM preparation is critical. You cannot stand up a compliant EVMS in Phase C if you haven't defined the WBS, OBS, and performance measurement techniques during planning. The risk register created in Phase A should capture technical, cost, and schedule risks and feed directly into the JCL analysis that must be completed before PDR. Teams that treat Phase A EVM prep as optional often spend the first 6 months of Phase C in a scramble to establish control accounts and work packages, and they permanently lose those months of performance data. Beyond the individual PP&C products, Phase A requires an integrated PP&C implementation plan, a document that defines how cost, schedule, risk, and EVM will work together throughout the life cycle. The key concept here is strategic partner. The PP&C team is not producing paperwork. It is making the decisions about how the project will be measured and reported for the next 4 to 10 years. KDPA requires defensible cost, schedule, and risk documentation, not finished products, but documented assumptions with clear rationale. The review board needs to trust the process, not just the numbers. Resource phasing by fiscal year is an output of Phase A PP&C work, and that phasing feeds directly into the PPB submissions that will determine whether the program receives the funding it needs in year 1. Phase B takes the Phase A concept and matures it to the level required for preliminary design review. Requirements are finalized, designs are validated, and the baseline for implementation is established. The shift from Phase A to Phase B is a shift from, is this feasible, to can we actually do this within cost and schedule? And that's a much harder question to answer, honestly. TRL6 is the Phase B exit requirement for critical technologies. You must be able to demonstrate prototype performance in a relevant environment before you commit to cutting metal. Phase B is where the PP&C baseline becomes real. The JCL, the IBR, and the integrated cost and schedule baseline must all be in place before KDPB, and they form the foundation of the agency baseline commitment. Requirements maturation and planning documentation updates are the backbone of Phase B, ensuring that what the project committed to in Phase A remains achievable, given what the design team has learned. Interface control documents, ICDs, and the acquisition strategy are the two most schedule-critical Phase B products that PP&C must track. A slipped ICD can delay subsystem work. A delayed contract can cascade through the entire IMS. Long lead procurements identified in Phase B require contracting actions that take 6 to 18 months. If you do not identify them early, you'll be managing a crisis in Phase C when hardware doesn't arrive on time. Programs that update their project plans and SIMPs in Phase B without updating the cost and schedule to reflect what the design maturation actually revealed end up committing to a baseline they cannot execute. This is the culminating activity of Phase B, the Joint Confidence Level Analysis, which mathematically integrates your cost estimate, schedule, and risk register to determine the probability of mission success. The PDR gate is the most important milestone in the project's life. This is where you've spent 50 to 60% of your budget, and now you commit to cutting metal. Get this wrong, and you own it for the rest of the life cycle. JCL at PDR must demonstrate at least 70% confidence. If it doesn't, you have 3 options: reduce scope, apply more reserve, or accept lower confidence, and all 3 require agency-level decisions. The Program Commitment Agreement, PCA, established at KDPB, is the document that governs the implementation phase. It is based on the products produced in Phase B, which means those products must be done right. Phase B cost estimating transitions from the rough parametric and analogy methods of Phase A to a more refined combination. Vendor quotes, engineering build-up for complex subsystems, and sensitivity analyses. Independent cost estimates, ICEs, are not optional. They're the cross-check that catches systematic bias in the program's own estimates. My experience at both JPL and Lockheed is that programs consistently underestimate the need for integration and testing. Cadre updates in Phase B should reflect what you've learned from preliminary design. If the cost grew, document why. If it came in under, explain that too. The review board expects the evolution to make sense. PPB alignment means your Phase B cost estimate cannot be merely technically correct. It must align with how funds actually flow through the government budget process. Phase, fiscal year, and appropriation category all matter. The Phase B IMS is no longer a high-level milestone schedule. It becomes a detailed, resource-loaded, logic-driven network that must support critical path analysis and schedule risk assessment, SRA. Schedule risk assessment integrated with cost risk is the critical new addition in Phase B. The SRA feeds the JCL, and the JCL is what the review board uses to assess whether the program is ready to commit. Mature the risk register with probability and consequence scoring in Phase B. The 5x5 matrix needs to be populated with real data from the engineering team, not placeholders from the project manager. A schedule that looks detailed but has never been resource-loaded or risk-adjusted will produce a JCL that is mathematically unsupportable. The review board will find it, and the program will lose credibility at the moment it can least afford to. Phase B is where the performance measurement baseline, PMB, is established and the Earned Value Management Plan, EVMP, is finalized. This is the EVM infrastructure that will govern Phase C/D reporting. The Integrated Baseline Review, IBR, conducted in Phase B is a joint government contractor review that validates whether the PMB is realistic and executable. If the IBR is not sound, neither is the KDPB approval. Standard reporting formats for variance analysis, EAC, and SPI/CPI trends must be defined and agreed upon in Phase B, not improvised in Phase C when performance data starts coming in. Early warning metrics and analysis books established in Phase B are the ongoing assessment infrastructure. They should be working by the first month of Phase C, not built from scratch after the first variance is identified. These 4 deliverables are the mandatory outputs required to pass KDPB, not nice-to-haves, but required products whose absence will prevent the gate transition. The final cost estimate becomes your budget, the final IMS becomes your baseline, and together with the JCL they form the agency baseline commitment, the one document that represents NASA's commitment to OMB and Congress. Each deliverable feeds the others. The cost estimate phases into the IMS. The IMS drives the JCL schedule inputs, and the JCL validates whether the integrated cost and schedule baseline is achievable at 70% confidence. By the time you have all 4 of these products of the quality required for KDPB, you have spent enormous resources on planning. That investment is the return on discipline. It prevents far more expensive surprises in Phase C/D. 7 planning disciplines form the full PP&C planning architecture. This slide maps the territory you'll cover in Module 1, from the fundamental question of why do we plan, through contracts. The planning phase answers 7 business questions. Where is the requirement? How is the work organized? What will it cost? When will it happen? How will we measure it? What could go wrong? And how do we buy it? As an analyst, you need baseline knowledge of all 7 disciplines, not deep expertise in each, but enough to evaluate whether the products being produced meet the standard required for gate transition. If you can only name these topics, but cannot describe what a good one looks like, you cannot do your job as a PP&C integrator. The rest of this module is about developing that judgment. Planning is not bureaucratic overhead. It is the mechanism by which complex multi-year programs provide direction, identify alternatives, communicate resource needs, and allocate finite budgets effectively. Failure without planning feels accidental, but it is not. When you skip the rigor of planning, the failure is predictable. You just haven't predicted it yet. Proactive responsiveness is the planning benefit that gets overlooked. Planning lets you see change coming and act on it before it becomes a crisis, rather than being driven by external forces. Resource allocation is the practical benefit that drives executive buy-in for planning rigor. When budgets are constrained, productivity is only maximized when resources are planned effectively, not when they're improvised in the moment. The first four steps of planning, scope, development approach, work organization, and work assignment build the structural skeleton of the project before any cost or schedule work begins. Steps 1 to 4 are sequential in logic, but iterative in practice. You define scope, then organize it in the WBS, then assign it in the RAM, and if the WBS reveals missing scope, you go back and fix the SOW. The outputs of steps 1 to 4, SOW, Integrated Management Plan, IPTs, OBS, WBS, WBS Dictionary, and RAM, are the foundation that everything else builds on. Flaws here cascade into every downstream product. Step 1 errors are the costliest. Missing scope in the SOW means missing cost accounts, missing schedule activities, and ultimately an overrun that everyone will call unexpected, but that was actually predictable from day one. Steps 5 to 7 translate the work structure into time and resource terms, scheduling the activities, identifying the resources required to execute them, and estimating what those resources will cost. Steps 5, 6, and 7 must be done in tight coordination. The schedule drives workforce phasing drives cost, and cost feeds back into whether the schedule is actually executable with available funding. Work packages and planning packages, step 6, are where the schedule connects to the financial system. This is where EVM lives, and these must be defined at the right level of detail to be measurable, but not so granular that they become unmanageable. The time-phased monthly cost profile produced in Step 7 is your baseline for budget execution tracking. If it is wrong here, phased incorrectly, based on optimistic assumptions, it will produce misleading analysis every month for years. The final two steps, negotiating and approving the plan, then analyzing and assessing its quality, are where the plan earns its legitimacy and where PP&C adds the most value. Doing the 9 steps doesn't guarantee a good plan, but not doing them ensures a bad one. Step 9 is what separates analysts who verify credibility from those who just document intent. Step 9 tools, EVM, schedule health checks, burn rate, JCL, are the validation battery that tests whether the plan created in steps 1 to 8 is actually executable. Use all of them before declaring the plan ready for baseline. The control account plan can occur by the PCM, PM, and line manager. Step 8 creates accountability. If the plan fails, you could trace it back to who signed off on an unexecutable baseline. This transition slide moves from the planning process overview to the first structural planning tool, establishing how the project is organized and how the work will be decomposed and assigned. The OBS and WBS must be set up correctly from the beginning. Fixing them after the fact is expensive and disruptive. It changes control accounts, reassigns work, and breaks schedule logic. The organizational question and the work breakdown question are not independent. The OBS determines who can authorize work in each WBS element, and errors in either propagate to every downstream cost account. Most programs that struggle with accountability problems in Phase C can trace the root cause to an OBS/WBS setup that didn't clearly define who owned what. This is the slide that prevents those problems. The organizational breakdown structure, OBS, is the hierarchical arrangement showing how project personnel are organized. It is the who counterpart to the WBS's what. The Space Shuttle Propulsion Office example here shows a real-world multi-tier OBS. Notice how each sub-office has a specific role and clear relationships. This clarity is what enables the RAM to assign responsibility unambiguously. Whether you organize by function, IPT, or matrix assignment, the OBS must reflect how work will actually be managed, not how leadership wishes it would be managed. Aspirational org charts create accountability gaps. The OBS combined with the WBS forms the responsibility assignment matrix, RAM, and the RAM is where cost accounts live. If the OBS is not right, the RAM is not right, and the control accounts cannot be properly managed. This continuation emphasizes that the OBS serves a dual purpose. It establishes accountability for work activities and provides the resource pool for schedule loading. You cannot ask who is responsible for this WBS element without an OBS. Without the answer, the RAM intersection point is empty, and an empty RAM means no one owns that work. The RAM intersection defines the control account, the lowest level at which scope, budget, schedule, and risk are integrated. Verify that every WBS element at the control account level has an organizational owner before calling the plan complete. OBS charts that do not reflect actual personnel assignments, showing positions that are vacant, matrix to other projects, or occupied by people without authority, create RAM accountability that exists on paper but fails in practice. The work breakdown structure is the product-oriented family tree that defines and organizes the total scope of work. It is the single most important planning document because everything else, cost, schedule, EVM, risk, contracts, hangs off it. The WBS is a framework for common reference across all project elements. When the schedule, estimate, and financial system all use the same WBS numbering, integration becomes possible. When they do not, chaos follows. Deliverable-oriented grouping is the design principle. WBS elements should represent things the project produces, not activities the project performs. When you see activity-based WBSs, you see control accounts that are hard to status objectively. The WBS is also the basis for IMS development, meaning that a poorly structured WBS produces a poorly integrated schedule, which in turn produces a poorly supported JCL, which results in a gate failure of PDR. WBS numbering and hierarchy define how work is decomposed from the project level down through systems, subsystems, components, and subcomponents, and every level rolls up to the one above it. The numbering scheme shown here, 1.0, 1.1, 1.1.1, 1.1.1.1, is the standard format, and it matters because the financial system, the schedule, and the risk register will all reference these same numbers. Inconsistent numbering breaks integration. As you go down the WBS hierarchy, level of detail increases, but level of detail should only go as deep as necessary to manage the work. The rule of thumb: go to the level where discrete, measurable work packages can be defined. The graphic format, boxes, versus the outline format conveys the same information differently. Know which format your program uses and why. Some teams find the outline easier to update, while others need the visual hierarchy to catch missing elements. NPR 7120.5 defines the standard Level 2 WBS elements for spaceflight projects. This is the template that establishes the common reference framework across all NASA programs. Every one of these 11 elements, project management, systems engineering, S&MA, science/technology, payload, spacecraft, mission operations, launch vehicle, ground systems, INT, education/public outreach, must be represented in the WBS if it applies to the project. The standard WBS ensures that independent cost estimators, review boards, and program offices all use the same structure when comparing your estimates with those for similar programs. Deviation from a standard requires specific justification. When evaluating a program's WBS, start with this chart and ask, are all applicable elements present? Are any missing? Are there any elements present that shouldn't be? Structural completeness is the first credibility check. The 100% rule is the single most important WBS quality criterion. The WBS must contain 100% of the work in the project scope, no more, no less, at every level of the hierarchy. When you're assessing a program's health, the WBS is a good place to start. Does it include all the scope? Does everything roll up properly? If not, you found a cost and schedule risk before it appears in the metrics. The 100% rule applies at every decomposition level. The sum of child element work must equal 100% of the parent. Any WBS that fails this test will produce cost accounts with missing scope, resulting in overruns that appear to be scope growth. The most common 100% rule failure is not adding too much. It is leaving things out. Project management, systems engineering support during integration, and closeout activities are the elements most frequently underrepresented or omitted entirely. The WBS dictionary provides the narrative description of every WBS element. It is the document that answers what exactly is included in this box for every node in the hierarchy. The dictionary is as important as the WBS itself. Where does electrical responsibility stop? At the main panel, or does it run power to the HVAC subpanel? The dictionary answers that. Without it, you have a coordination gap waiting to happen. A well-written WBS dictionary defines scope, interfaces with other WBS elements, and management intent for each deliverable. When it is missing or superficial, control account managers disagree about who owns the work, and that disagreement surfaces as a cost variance. During an IBR or peer review, reviewers will ask control account managers to explain the scope of their accounts. If the managers cannot answer from the dictionary, or if the dictionary doesn't reflect the actual work plan, the baseline lacks credibility. The RAM is the intersection matrix that maps the WBS, what against the OBS, who. The intersection points define the control accounts, which are the basic unit of performance measurement in EVM. The control account is where your budget, schedule, and performance measurement all meet. Work packages and planning packages live below the control account. This is where EVM data is generated and where the integrator focuses. Each control account has a manager, CM/PCM, who is accountable for the account's scope, schedule, cost, and risk. If the PCM doesn't understand what they own, the control account will not produce credible performance data. The RAM diagram shows both the WBS hierarchy and the OBS simultaneously. When you lay them on top of each other and identify every intersection, you've completed the accountability framework for the entire project. This is the analyst checklist for evaluating whether the organizational and work structure has been set up correctly. The questions that determine whether a program is ready for the next phase. All 6 questions point to the same underlying risk. If the WBS/OBS structure cannot support EVM, JCL, and scheduling, then the program will spend Phase C trying to retrofit control mechanisms into a baseline that was never designed to support them. Is it logical? Does it capture all scope? These are deceptively simple questions. The answer requires walking the WBS element by element against the SOW and verifying every shell statement is captured somewhere. Answering yes to all 6 questions is not the end of the assessment. It is the starting point. A WBS that is logical, complete, and structured correctly is a necessary but not sufficient condition for a credible plan. This transition slide moves the module from work structure to the cost dimension, the discipline that quantifies what resources the organized, scoped work will actually require. Cost estimating and pricing are different disciplines and should never be confused. Pricing is contractual multiplication. Estimating is the careful analytical judgment of what it will actually take to do the work. The quality of your cost estimate determines the quality of your JCL, which determines whether you can make the commitment to Congress. Weak estimates yield weak JCLs, which lead to gateway failures. As an analyst, even if you do not develop estimates yourself, you need to understand how they were developed so you can evaluate whether the method was appropriate, the assumptions are reasonable, and the number is defensible. The distinction between estimating and pricing is fundamental. Pricing is a contractual calculation based on pre-agreed rates, while estimating is the analytical judgment of actual resource requirements within a defined scope. The paint room example is exactly how to think about estimating. You have to think through every input: square footage, coverage per gallon, number of coats, materials, labor hours. Skipping any input means your estimate is incomplete. Assumptions are the key to any good estimate, and documenting them is what separates an estimate that holds up a review from one that falls apart when the review board asks, "Why did you assume that?" The failure mode here is treating estimating like pricing, applying a rate to a quantity and calling it an estimate. That approach hides the actual cost drivers and produces a number that has no basis in the work content. 3 cost estimating methods define the estimation landscape: top-down parametric, analogy, and bottoms-up/grassroots, each requiring a different level of design definition and producing a different level of precision. The key insight is that more data is required as you move from top-down to bottoms-up. You use the method appropriate to what you know, not the method that produces the answer you want. The perception that bottoms-up is always more accurate is a common misconception. Early in the life cycle, a well-calibrated parametric model drawing on hundreds of historical programs can be more accurate than a bottoms-up built on incomplete requirements. The appropriate method depends on where you are in the life cycle and what data you have. Using a bottoms-up approach in phase A when you do not have design definition produces false precision. The estimate looks more rigorous than it is. This chart illustrates how the prevalent cost estimating method changes over the project lifecycle, from parametric in phase A to a mix in phase B to bottoms-up and actuals in phase C/D. The shift makes intuitive sense. In phase A, you have a concept, not a design, so you estimate from analogs and models. In phase C, you have drawings, hardware, and actuals, so you estimate based on what you know. The transition between methods must be managed consciously. As the project gains definition, the parametric baseline should be validated against bottoms-up estimates for the key cost drivers. Discrepancies require explanation. Review boards know this chart. When they see a Phase C program using parametric estimates for major subsystems that have been in fabrication for 2 years, they ask why, and the answer usually reveals something about the quality of cost controls. This chart illustrates how the prevalent cost estimating method changes over the project lifecycle, from parametric in phase A to a mix in phase B to bottoms-up and actuals in phase C/D. The shift makes intuitive sense. In phase A, you have a concept, not a design, so you estimate from analogs and models. In phase C, you have drawings, hardware, and actuals, so you estimate based on what you know. The transition between methods must be managed consciously. As the project gains definition, the parametric baseline should be validated against bottoms-up estimates for the key cost drivers. Discrepancies require explanation. Review boards know this chart. When they see a Phase C program using parametric estimates for major subsystems that have been in fabrication for 2 years, they ask why, and the answer usually reveals something about the quality of cost controls. Cost models, both commercial COTS, like Price, SEER, and CACAMO, and NASA-specific like PCC, SSCM, and CM, are the tools that implement the parametric estimating methodology. Models can be made to tell you whatever you want to hear. Adjusting knobs until the model produces the right answer is how optimism gets embedded in estimates that later justify overruns. All COTS models must be calibrated, fed historical project data from programs similar to yours, and validated to ensure they produce reasonable answers for your mission class before you use them for a JCL input. The failure mode of model misuse is subtle. It doesn't look like dishonesty. It looks like subjective input set to reasonable levels by people who have a stake in the estimate being low. No single model does everything well. Different models are optimized for different cost drivers, and using the wrong model for your mission type produces estimates that are misleading in ways that are hard to catch. A good rule: do not use a spacecraft model to estimate the cost of a lunch. The principle applies directly. Use each model only for what it was designed to do, and use multiple models to cross-validate the major cost drivers. The range of values that models produce given different inputs is the uncertainty band, and that band should directly inform your UFE, management reserve, sizing. If the model produces a wide range, your reserves should reflect that uncertainty. Subjective inputs like heritage and complexity are the analyst's responsibility to challenge. They're the levers most easily adjusted to produce a desired answer, and their settings should be documented and defensible. The GAO Cost Estimating and Assessment Guide is the external reference standard that government review boards use to evaluate whether an estimate meets professional credibility standards. The GAO Guide codifies what a good estimate looks like: well-documented, comprehensive, accurate, and credible. If your estimate doesn't meet GAO criteria, you'll find out at the Standing Review Board. Knowing this guide exists and what it says is a basic professional competency for PP&C analysts who work on programs above the JCL threshold. Review boards draw their evaluation criteria directly from it. The guide covers not just technical accuracy, but process quality. How was the estimate developed? Who reviewed it? What assumptions were made? And how were differences with independent estimates resolved? The basis of Estimate, BOE, is the documentation package that explains how and why a cost estimate was developed. It is the audit trail that makes an estimate reviewable, reproducible, and defensible. A good estimator will have a good BOE. If you're reviewing a program and the BOEs are thin, superficial, or missing, that suggests something about the quality of the estimates they support. 6 characteristics define a good BOE: well-documented, comprehensive, credible, traceable, accurate, and executable. An estimate that passes 4 out of 6 is not passing. All 6 are required for a defensible baseline. BOEs should be updated whenever estimates change and whenever a new PPB submission is prepared. A BOE that reflects the initial estimate but not subsequent re-estimates is documenting historical intent, not current commitment. The standardized BOE template captures all the elements that make an estimate reviewable: WBS reference, project manager, doing organization, assumptions, rationale, labor, material, ODCs, and time phase cost by year. Standardized templates matter because they enforce consistency. When reviewers know exactly where to find the assumptions and the doing organization, they can complete a BOE review in a fraction of the time it takes to parse a non-standard format. The template's value is in the assumptions field. This is where the BOE proves its credibility. If the assumptions are vague, circular, or untested, the cost estimate built on them cannot be defended at any serious review. The person actually performing the work should create the BOE for their cost account. They know what it takes to do their task. When someone else creates it on their behalf, the assumptions are likely to be wrong. The GAO criteria for BOE assessment: well-documented, comprehensive, accurate, credible, and traceable, define the minimum quality standard that program offices and review boards apply when evaluating estimates. Repeatable is the criterion that separates a real estimate from a number. If someone else runs the same calculation and gets a different total, the estimate is not credible. Show your math, document your tools, and make the calculation reproducible. As an analyst reviewing a contractor's BOEs, start with this sums criterion. Do the BOE details actually add up to what was submitted in the PPB? Basic arithmetic errors in contractor financial packages are more common than people expect. The BOE assessment criteria provide a structured framework for variance analysis as well. When a cost overrun occurs, the root cause is often traceable to an assumption in the BOE that turned out to be wrong. 10 questions form the analyst's cost estimate assessment checklist, the practical evaluation framework for determining whether an estimate is ready to support a gate decision. Is the estimator credible? Is listed as a criterion because I know from experience that the source matters. An estimate produced by someone who doesn't understand the technical content of the work is unreliable, regardless of how well documented it appears. Does it reconcile well with other cost estimates such that you understand what drives differences? Is the integration question. Independent estimates will differ, but you should be able to explain why, not just accept that they do. These questions are most useful early, before the estimate becomes embedded in the PPB and the baseline. A no answer at review is recoverable. A no answer discovered during execution means you're already living with the consequences. This transition slide moves from cost to scheduling And the opening question frames the scheduling discipline correctly. It is not what scheduling software should I use, but what does this project actually need from schedule? The importance of setting up the project WBS and financial WBS correctly before scheduling. If the cost accounts aren't right, the schedule cannot be properly resource loaded and EVM will be meaningless. The schedule is one of the most, if not the most, important tools for analysis and assessment. A poorly constructed schedule in Phase B will produce misleading analysis every month during Phase C/D execution. What kind of schedule do I need? Has a concrete answer. One that is integrated with cost, supports EVM and JCL, passes health checks, and reflects the actual technical work plan, not a calendar of meetings and milestones. Scheduling does 5 things. It measures performance against baseline, identifies potential risks, supports what-if scenarios, analyzes workaround options, and forecasts start and completion dates. A key insight: schedule development is an iterative process. The schedule you build at the start of Phase B is not the schedule you'll have at PDR. It evolves as requirements mature, risks are identified, and the design stabilizes. What-if scenarios is the analytic capability that transforms a schedule from a tracking tool into a decision support tool. If your schedule cannot answer, what if supplier X slips 3 months? It is not serving its highest purpose. Forecast start and completion dates is where the schedule earns its credibility. If the schedule consistently forecasts incorrectly, it is either not logically integrated or not being maintained with accurate status. The IMS consists of 3 tiers: master schedule, intermediate schedules, and detailed schedules, control account, and work package levels, with both vertical and horizontal integration linking them together. Horizontal integration is the critical path and logic flow across time. Vertical integration is the roll-up from detailed activities to the master schedule. Both must be present, or you do not have an integrated schedule. The tier structure is not cosmetic. Each tier serves a specific decision-making audience. The master schedule communicates to agency leadership. The intermediate schedule supports program management. The detailed schedule is where the work is actually managed. Programs that maintain only the master schedule and call it the IMS do not have an integrated schedule. They have a milestone list. When things go wrong, they have no visibility into what's driving the schedule problem. Level of detail must be matched to the project's need for control, not so high that the schedule becomes unmanageable, and not so low that it cannot identify problems before they cascade. The WBS dictionary will help you identify the discrete activities in each WBS element. If the dictionary is good, you already know how detailed the schedule needs to be at each level. Level of detail must be discrete and measurable is the performance measurement requirement. An activity that cannot be objectively measured as complete or incomplete cannot support EVM. It produces subjective percent complete estimates. Rolling wave planning is the practical solution. Plan the near-term work in detail and use planning packages for work that's far enough out that the definition is not complete. Convert planning packages to work packages as you get within 6 months of the work. Resource loading is the process of assigning all required resources, people, equipment, materials, subcontracts, facilities to schedule activities so that the schedule reflects what it will actually cost to execute. Bill's note: the debate over what resource loading means continues. In the JCL world, resource loading specifically means cost loaded. Know what your program's definition is and what your contract requires. The schedule without resource loading answers when, but not what will it take. An unloaded schedule is useful for milestone tracking but cannot support budget phasing, workforce adequacy analysis, or JCL calculation. The cautions against resource loading are real. Inadequate tools, undefined resource pools, and resistant team culture are all valid obstacles. But the alternative, no resource loading, means the schedule and budget are never validated against each other. 4 benefits define why resource loading is worth the effort. It validates that the schedule is achievable with available resources, supports management decision-making, enables resource reallocation, and flushes out cost-schedule integration errors. Unless resources are applied to the schedule, there is no way to determine if the schedule is achievable or efficient. This is why programs that skip resource loading end up with schedules that look executable on paper, but collapse during execution. Resource leveling, the process of resolving resource overcommitment, is only possible if resources have been loaded in the first place. Programs that skip loading skip the ability to detect overcommitment before it causes schedule slippage. NASA doesn't always do full resource loading, as Bill notes, but that doesn't mean it is optional on programs above the JCL threshold. Know your program's requirements and push for resource loading where it matters most. The critical path. The schedule baseline is the approved, realistic execution plan. It must be endorsed by the project manager, based on the technical plan, and integrated with the budget before it can serve as the foundation for performance measurement. I need to emphasize that the schedule baseline is the basis for the initial EAC. If the baseline is wrong, either over-optimistic or out of sync with the budget, every EAC you produce will be wrong from the start. Realistic is the critical word. A baseline is not realistic because leadership says it is. It is realistic when it has been validated through resource loading, health checks, risk-informed margin, and a credible JCL. Do not baseline too soon is important practical advice. A baseline established before the design is sufficiently mature will require immediate rebaselining, which undermines performance measurement integrity and erodes credibility with the review board. This slide presents the fundamental question and then answers it with the analyst validation checklist, the 8 things you must verify before a schedule can be called credible and executable. Each of the 8 validation criteria is a known failure point for programs that I have observed or led. Unrealistic durations, missing external deliveries, illegitimate constraints, and insufficient margin are the 4 most common sources of schedule baseline collapse. Validate vertical and horizontal traceability is the integration test. It ensures that the detailed level rolls up consistently to the intermediate and master schedule levels, and that the logic network flows coherently across time. Scheduled health checks are your ongoing early warning system after baselining. Use them monthly, not just during milestone reviews. They'll surface emerging logic problems before they become critical path problems. Just as cost estimates require BOEs to document their rationale, schedule durations require BOEs, specifically documentation of how durations were determined, what assumptions were made, and what risks were factored in. How do you know it takes 3 months to perform a certain task? If the answer is the scheduler estimated it, that's not a BOE, that's a guess. A BOE traces the duration to historical data, analogy, or expert assessment. The schedule BOE template mirrors the cost BOE. It captures the doing organization, assumptions, rationale, and time phase commitment. Without it, you cannot defend the schedule duration when the review board asks. BOEs for schedule are frequently the weakest part of a program's planning package, and they're the first thing a standing review board examines when schedule credibility is in question. 8 questions define the schedule credibility assessment. This is the analyst checklist for determining whether the IMS is ready to support a gate decision and serve as a performance measurement baseline. Will schedule allow EVM? Will schedule allow JCL creation? Are the integration tests that reveal whether the schedule was built to enable decision support or just to satisfy a documentation requirement? Does it make sense at 10,000 feet and appear executable? This is the common sense test I emphasize throughout this course. If you cannot explain the schedule's shape to someone unfamiliar with the project, it probably doesn't reflect the actual plan. The closing statement matters. An integrated cost/schedule baseline is a requirement to transition from planning to implementation. This is not a suggestion, it is the gate criterion. Don't move to phase C without it. EVM is introduced with Dr. Graham Edwards' quote, "It's not the plan that matters, It is the planning. To reframe the purpose of EVM, the discipline of planning produces the baseline that makes objective performance measurement possible. EVM is required for all projects in Phase C/D with a lifecycle cost greater than $20 million. But the real value is not compliance. It is the early warning system that tells you where you are and where you are headed before problems become crises. The ANSI/EIA 748 standard defines the 32 criteria that a valid EVMS must meet. Knowing which criteria are at risk in your program is a basic analyst competency, and the IBR will test each. Programs resist EVM because it reports reality, and reality is often uncomfortable. My response is that's exactly the point. Comfortable illusions during execution become expensive surprises at delivery. The regulatory requirement table defines exactly which programs must implement EVM and to what standard. The $20 million threshold for Phase C/D programs is the baseline, with higher thresholds triggering validated EVMS requirements. Even if EVM is not contractually required, you still need some mechanism to determine performance, a tailored performance measurement system that serves the same function. There's no acceptable substitute for measuring whether you're doing what you planned. The requirement also applies to phase E modifications above $20 million. This is frequently overlooked by programs that completed their IBR years ago and believe their EVM obligation is behind them. The thresholds change periodically. As an analyst, verify the current threshold for your program class and appropriation type. Do not rely on what was true for the last program you worked on. EVM provides the current status answer by integrating three dimensions: technical milestone accomplishment, schedule performance, and cost performance against the approved baseline. My emphasis: EVM answers, where are we today? This is why upfront planning matters so much. Your analysis and assessments through the life cycle will be measured against the plan you develop in planning. Get the plan wrong, and every EVM report is wrong. Are we meeting our technical milestones? Are we on schedule? Are we within plan cost? What are the variances? Why are there variances? Is a trend forming? These 6 questions are the monthly rhythm of the control analyst job. Notice the questions start with technical milestones, not cost. This is intentional. Cost variance is often a lagging indicator of a technical problem that was visible earlier in the schedule. Start with the technical story. The forward-looking dimension of EVM, analyzing current trends to forecast completion cost and schedule, is where EVM delivers its highest analytical value and supports corrective action decisions. Christensen's study finding: once you are 20 to 25% into your project and your variance exceeds 10%, you will almost never recover more than 10% of that deficit. The trend tells you where you are going. What should we do now to mitigate problems? Is the call to action. EVM is not just a reporting tool. It is a decision support system. The analysis of trends should produce specific options for the project manager to consider, not just data summaries. Is it achievable? Is the question that EVM honestly forces onto the table. A project that is behind schedule and over cost in month 8 of a 48-month program has a performance trajectory, and EVM makes that trajectory visible to everyone in the room. EVM provides early warning by combining objective measurement of technical accomplishment, schedule performance, and cost performance into an integrated picture of project health. Reporting and analysis is most efficient when levels and thresholds are carefully crafted. This is the analyst's setup instruction. Thresholds should be set based on the program's size and risk profile, not copied from another program without thought. Communicates progress to stakeholders and project management for effective decision-making is the outcome statement. EVM data that doesn't flow into decisions has failed its purpose. It is generating reports, not producing insight. The three-legged stool metaphor: technical, schedule, and cost performance each support the overall project assessment. Measure only 2, and you have an unstable picture. EVM integrates all 3. This slide addresses the setup paradox. EVM reporting doesn't start until Phase C, but the EVM system must be established during planning. You cannot retrofit compliant EVM infrastructure onto an improperly structured baseline. The key takeaway: if you're going to use EVM throughout your life cycle, you must set it up during your planning phase. The WBS, OBS, RAM, control accounts, work packages, and PMTs all have to be in place before you get your first month of performance data. The analyst needs to understand the EVM requirements and ensure the EVM system is in place and operational by Phase C. This is a planning deliverable, not an execution deliverable. Programs that rush into Phase C without a functional EVMS spend the first 3 to 6 months establishing control accounts, defining work packages, and negotiating performance measurement techniques, while real performance data is going uncaptured. This slide addresses the setup paradox. EVM reporting doesn't start until Phase C, but the EVM system must be established during planning. You cannot retrofit compliant EVM infrastructure onto an improperly structured baseline. The key takeaway: if you're going to use EVM throughout your life cycle, you must set it up during your planning phase. The WBS, OBS, RAM, control accounts, work packages, and PMTs all have to be in place before you get your first month of performance data. The analyst needs to understand the EVM requirements and ensure the EVM system is in place and operational by Phase C. This is a planning deliverable, not an execution deliverable. Programs that rush into Phase C without a functional EVMS spend the first 3 to 6 months establishing control accounts, defining work packages, and negotiating performance measurement techniques, while real performance data is going uncaptured.